as you would have seen by virtue of the invite, for those of you who do read the invites and register, our guest speaker for tonight is a gentleman, as you can see here, named Peter Stokes, who's the director of CMC Microsystems. And this organization has a fascinating story, which I'm not going to tell, Peter is, but they originally founded in the early 1980s and have done, similar to kind of my last framing there, some pretty significant things in terms of helping Canadian tech companies get on and stay on at the front of, in many cases, a segment of the technology landscape. And as we look forward, as the move to ever more microscopic, nano-type technologies, CMC is still here today and enabling a lot of that advanced, innovative thinking. So without further ado, again, I'd like to introduce Peter Stokes from CMC Microsystems.
Good evening, and thanks for coming out. Indeed, it's a pretty neat organization, CMC, that I work for. Just to pick up on that story, in the early 80s, late 70s, a number of professors at Queen's University said, you know, it'd be really cool, instead of just designing our chips, we could actually manufacture our chips. And they knocked on the door of Nortel on Moody, and they said, hey, you guys make our chips? And Nortel said, yeah, okay. And so they did that. They made chips, they fabricated them, they published papers. And of course, a researcher's paper is much more well-received, higher citations and so on if you actually make a part and test it. And they said, you know, that was fantastic, we should do that again. So they ran a workshop and they were overwhelmed with attendance. And Nortel said, well, we'll make more chips, but look, we don't want to be dealing with every graduate student and every professor that wants to do this across the country. And so they created the Very Large Scale Integration Center at Queen's University. That became CMC Microsystems. So that's the backstory there. How many people, just quickly, have heard of CMC in the room? Quick. Wow, okay, quite a few, show of hands. So we're not the Canadian Marconi, right? We're not CMC Electronics, we are CMC Microsystems, we're in Kingston. And maybe a little bit of background on me. So after school, I went and worked at Dypix. Anybody remember Dypix here in Ottawa? Show of hands, yeah, a few people? Yeah, excellent, cool. So I worked at Dypix and hardware design for a little while, then I went to Novotel in Brockville, and they shut that down, and then I started working at CMC in the early 80s. So I've been there a long time. One of the neat things about working at CMC is I've been a spectator to some really cool research going on all across Canada. And I just want to share a little bit about that with you this evening. So I live in Kingston. I'm there with my wife. I've got a daughter, just finished second year at university, and we're really enjoying it there. CMC is a fantastic organization to work for. And you're probably wondering what the connection is of me in this picture. Can anybody guess? I took the picture. Somebody said that, right? That's exactly right. So I used to run Fairmount. My knees told me to stop. But as a hobby on the weekends and stuff, I'm a volunteer photographer, and I love to justify my expensive equipment by going out and taking pictures. So I do this a lot. So if this presentation isn't working for you, you can go to peterstokes.net, N-E-T, and you've got my whole gallery there. This is the Beat Beethoven run. So this was 2 days ago, 3 days ago on Sunday in Kingston. This is downtown Kingston, beautiful city. And there's 700 people in the field here, so it's a huge, long line of people ready to start the race here. And if you look on the left here, you can see the Fort Henry Guard, right? So they fire the gun, or whatever you call that thing, the rifle. And musket? Yeah, thanks. And so as a photographer, I was really, really pleased. I hit the shutter button just at the right time, because you look really carefully, you can see the sparks coming out of the gun. Maybe you can't see it on this thing here, but you can actually see the sparks coming out of the rifle if you go to my website. Okay, so that's a little bit of background on me. So we're just going to dive into the presentation. So here's a rough agenda. A little bit about CMC, the corporate stuff, and then I'm going to talk a little bit about what we do and how we can help startups and how we can help university professors. And then I've got a deal for you if you came with 100K, just in case you did. Some of the fame and glory of others, and then a couple of topics that I know very little about, which is a dangerous thing to do, but I do want to touch on them. It's a couple of examples of the cool stuff that I see. What I'm wondering is there anybody in the room who's familiar with photonics design? Done any kind of photonics? Sir. And your name is?
Leo.
Leo. All right, so when we get to that part, if there are any questions, Leo's going to handle them. All right, Leo? Okay. So Leo, 5B is the photonics part. Because I have no idea what this chip does, how it works, or anything, but I've got really cool pictures. Thanks, Leo. All right, so we're going to dive into this. A little bit about CMC. So again, we're a not-for-profit incorporated in 1984. I think I joined in 1983, just before it became a corporation. We manage what we call Canada's National Design Network. We're a happy group of around 40 people. We have offices in Ottawa. We're opening an office in Montreal. And we've got the majority of the employees, is the picture on the left here, based in Kingston. And we support the Alzheimer's Society in a big way. We've raised over $100,000 over a number of years for them, with our auctions and so on. And this is just a picture of the staff there. So 2/3 of the employees are engineers and scientists. Okay, so we've got people with engineering, physics, electrical engineering, computer engineering, maybe mechanical engineering. So we've got a pretty talented crew in there. And what we do is we help researchers across Canada and startups to design chips, to manufacture chips, and to test chips. So that's what I want to describe to you today. So there they are: design tools, fabrication services, equipment for testing those chips, platform technologies. Maybe there's something that you want to use in your chip somebody else has done, so you can just stand on the shoulders of that work and incorporate it into your chip. You can download that from our website, training, support, networking, and then we can also connect you with researchers across the country who have topics of interest that may match with yours to collaborate. I was told that we're going to have quite a diverse crowd in the room, so I dropped this slide in here. So what are microchips? Well, the microchip is that small device you see just to the left of the one on the penny there.
What's a penny?
Yeah, what's a penny? That's right. And that's actually a chip. That's actually a chip we helped to manufacture this. So that's a iSpy is the name of the company, and then Waterloo, University of Waterloo spinoff. And it's a detector, and it's actually got a cantilever, and that cantilever will measure, I think it's surface topography through electrostatic, I think means. It's a MEMS device, all built in, smallest device of that time ever, a world record, and we helped to manufacture that. So a microchip is a small device that you find in cell phones. It's things that you find in controlling the timer in your toaster. It's running the Internet of Things and so on. So used in all sectors. So CMC Microsystems runs what we call Canada's National Design Network, and we're the manager of that. And so what we did is we drew a circle around all of the researchers, all of the companies, and then all of the facilities, and we call that Canada's National Design Network. And there it is, 66 universities, and one of the cool things about my job is I get to travel, and I have been to about 50 of them, which is pretty cool. And I've been to many of them multiple times, but I've been to about 50 universities. I've got a running tab, it's around 50 right now, over the years. So it's a really neat way to see all of Canada. So we've got 66 universities, 950 companies is a 5-year rolling average on that, or a 5-year total, that work with researchers that we support and work with us directly, a smaller fraction of those. And they form what we call Canada's National Design Network. And our bottom line are these kinds of numbers, right? So as a not-for-profit, funded through government sources, through user fees and other means, journal publications, national awards, international awards, startup companies, patents, licenses, interactions with industry, and so forth. So that's our bottom line as a not-for-profit. Our primary interest is a thriving industrial sector in Canada around using integrated circuits. And we've seen that over the years. So there's very likely that a company you work for, if it's got anything to do with chip design, has HQP, highly qualified personnel, that use the CMC program. Is there anybody in the room by chance that uses the CMC program? No, maybe not. Okay, quite often there is one or two. They go, oh, yeah, I remember when I was in university, I made a chip, blah, blah, blah.
No one's saying nothing after the wheel.
That's right. So, about 1,000 faculty, right, use our services, 1,000 professors, and each one of those professors has 2.5, 3.5, I can't remember the number, is the average graduate students. I mean, some have 20 and some have 1. And so we have a lot of neat data on them, and there's just a quick snapshot here of the technology application area, so you can, well, I don't have to tell this crowd, there's a chip in just about everything now, right? There's chips in cars and toasters and cameras and cell phones and your chair probably someday. So of the technology applications spread around there, of the researchers who work with us, their design-oriented interests, and for those who can't see from the back of the room, you know, embedded systems, quantum, nano, photonics, microfluidics, MEMS, embedded software, mixed signal, analog, RF, digital, and molecular. So this is all the topic areas of interest to those 1,000 faculty, and then the disciplines and the departments in which they operate. And so it's about 50% electrical computer engineering, and then the chips are also being used in a whole bunch of other disciplines. So over the years, we've seen the pie growing larger, but the proportion of electrical computer engineering slowly shrinking, and that's because chips went from just something you do in electrical to something you do in mechanical. I mean, people are throwing chips in cement while they pour it to build a bridge so they can sense, you know, I mean, they're just about everywhere. All right, so why would this network be important? We're just closing off on the About CMC here. And that, well, I mean, we know the answer here, right? If you look on the far right-hand side here, that column, you see the economic strategy tables. That's our government here in Ottawa, the federal level government saying these are important areas for Canada. They voted with their wallet with the superclusters, which I'm sure you've heard about, and then CMC's areas of technology application down the left-hand side there. So there's a very strong link with the program we offer, the people we train, the chips we manufacture, the startups we help, and the economic benefits for Canada. So I'll just use that moment too. I mean, somebody came to me just before I started and said, I thought you guys shut down. Yeah, we had a near-death experience. We sure did over the last couple of years. The funding, the way funding turned out from government, we ended up with having to issue layoff notices to all employees, and we were in that state for about 6 months. But we lobbied hard, and the government pulled through. We thank Industry Canada, and we thank Canada Foundation for Innovation. So we've secured funding. We're in really good shape now. We're looking excellent shape, actually. We have a lot of capacity for chip manufacturing. So if somebody wants to make a chip, I've got a pile of business cards right there on the table. Startup or university or both, a collaboration. Business cards are on that table. We'll make your chip for you at rates which are quite competitive. So I think we're going to hold questions to the end, unless that's for Leo.
I was going to ask, how long is the funding for? 5 years?
It's a whole bunch of overlapping funding. Okay. So right now we're good for about a year on our operating. We're good for 2.5 on some capital. The user fees are rolling, obviously, year to year. We're currently in the throes of an application for more funding, or more operating funding. We feel pretty good about that, so things are looking pretty good. We're, in fact, in hiring mode now. The next question is for Leo, she promises. All right, make it a photonics question. Okay, I will move on. And so this is Canada's nanotechnology ecosystem at a glance. You can see CMC is the third icon from the right there. But, you know, C2MI in Quebec and INO in Quebec, and then it just goes all the way across the country. I mean, Canada doesn't have a big fab. Does anybody remember the initiative to bring a fab to Ottawa? Does anybody remember that? That was yeah. We don't have a big fab. We do have some interesting facilities, though, like Celestica does some cool stuff. Microline at Edmonton does cool stuff. In Bromont, Quebec, we have Teledyne Zulsa. We have an IBM packaging facility there, which is world-class. C2MI, as I mentioned, so there is some stuff going on here. But buying chips made overseas is the way that anybody goes these days, right? I mean, chips are primarily made in Taiwan, right? TSMC is one of the largest, and Global Foundries and ST and so on. All right, and we'll now talk a little bit quickly about what I call making it big by making it small. So the smaller and smaller the chips are, the better and better they perform, and the more success that a professor or startup or a company will have in terms of success. So we're just going to dive into that. We divide our products and services across 3 lines, business lines, lines of business: CAD, Fab, and Lab. So the CAD is the design tools for designing chips. The Fab is the service for manufacturing those chips. What does that mean? You send us a file, and a few months later, we send you a handful of chips. And then you've got to test those chips, and so we have equipment that we make available for testing those chips: VNAs, VNCs, oscilloscopes, and so on and so forth. So those are the 3 primary lines of business, and our customers are 90% university professors and 10% companies and startups and so on. We do private fabrication runs for companies that's never on our fab schedule or anything. And the other thing we do is we help a lot of professors working with a startup, or a professor who is starting a startup. We'll make chips for them. So I'm just going to walk through those really quickly. There's about 50 suites of CAD tools. That number's not on there, I don't think, but it turns out to be around 50 suites of CAD tools. So if you're familiar at all with the chip design world, Cadence, Mentor, Synopsys, Ansys, so on and so forth, COMSOL, et cetera. So we have all of those tools available. And over the years, we've developed a pretty cool system where we now only need to buy as many software seats as there are active users nationwide, right? So we have a national sharing system now. So when a graduate student stops using a piece of software, say a console seat in University of Victoria, when she shuts that down, a student at Dalhousie will be able to pick up that software seat and start to use it right away. So we've got a pretty cool system set up. Non-trivial, let me tell you, to set that up in the background. But it gets about a 3x efficiency improvement, right? So we can buy 1/3 the number of seats, 1/3 the support to support that number of users. And what that means is more software, more variety, more things to explore. So there are the software tools. You may recognize some of those: ANSYS, Altium, ARM, Cadence, Keysight, so on and so forth. And what's been really big over the years, last 10 years or so, we have distinct Canadian competitive advantages around photonics. And I've got a little bit more on that coming, but we do have a design platform, Photonics. So we've got a variety of tools, some IPs, some process design kits, and manufacturing of photonics chips. So you literally send in us a file, we send you back a photonics chip. We've got that all working, as I mentioned, in an IT cloud infrastructure. You can see a picture of that. So it's your usual diagram showing a lot of CPUs and so on and so forth. But we're finding there's a crowd out there that's interested in accelerating EDA or accelerating whatever it might be using, say, an FPGA plus a GPU plus a CPU, right? And so we've built a cluster around that, and I've got a little bit more on that coming. So we'll just dive into the chip fabrication services. About 25 different sources that we get worldwide. So if you want a chip made in TSMC 65 nanometer CMOS, we'll have that chip manufactured in Taiwan. If you want a ST 28 nanometer CMOS, that'll be manufactured in France. If you would like photonics chip manufactured, we will make that in Singapore at AMF. We have all of the supply chain set up to do that in prototype quantities for research. And the efficiency gain here, unlike in the CAD, is around what's called the multi-project wafer. And so, actually, I have a wafer here. Is there a school teacher in the room, by the way? Like public school, elementary school? All right, I'm going to give you this wafer, sir. Anybody remember ATI in Toronto, right? There you go.
Can I ask me a question like Leo?
No, Leo's not taking questions right now. The reason I give that to you, sir, is because it's actually pretty cool. And if you could take that to your classroom, or if it's your partner who teaches, yeah.
I think software, but then...
Yeah, so ATI in Toronto, I knew somebody there. It's now AMD, right? Anyway, so he gave me a whole pile of these, and they're great to show kids and so on and so forth. Anyway, maybe pass it around. Hope you get it back. Multi-project wafer is where, unlike in that there, where that's ATI, so video chips, right? So there's a GPU, GPU. So typically on a wafer, you'd have the GPU repeated all over, right? In a multi-project wafer, as you can see on the left here, you have design A, B, and C, which are from different places, right? So design A could be from a startup, design B could be that student at U Victoria, and design C could be that student at Dalhousie. And so her chip is there, and his chip is there. And we bring them together, we merge them together, and then we manufacture them, and then we singulate them. We actually cut the wafer up, and we liberate a few of the chip for the person at UVic, and a few for the startup, and a few for the Dalhousie. We ship them out that way. And so for the price of one set of masks, the most expensive part of manufacturing a chip, you get multiple users. 30 or 40-year-old concept used by about 10 organizations worldwide, and of course the big chip manufacturers. We use that method as well. So where do we have chips made? Well, we partner with CMP, with Moses in Europe, TSMC in Taiwan. We have Europractice, which is a European program. We partner with them. Microline in Edmonton, SC Microelectronics in France, Global Foundries in the United States, Teledyne, Dulce, and Bromont. It goes on and on. We make photonics stuff at NRC here on Montreal Road, CEA Leti in Europe as well, IBM, the list goes on. So access our website, you can see the fabrication schedule, start on your chip. The other thing we do is in Canada, there's a variety of estimates, but it might be $500 million worth, $500 million worth of micro-nanotechnology manufacturing equipment in universities. So Carleton has a capability. University of Ottawa here, for example, has a capability, especially in the area of photonics. And so we work with those university labs as well, and that's where you might take a chip, let's say that we manufacture at ST Microelectronics, and bring it into the lab and post-process it, do something really weird, add another layer, maybe put some sensor technology on top. And so we work with the university labs. We provide financial assistance too, so if somebody's interested in accessing labs, we can help to offset the travel costs and the time, the material and machine time costs accessing that lab. So I mentioned photonics as being something that we kind of left, the way it's been described, we left that open loop. So when we saw interest growing in photonics about 15 years ago, we said, that's interesting, so let's just leave it open loop, and when people ask for more for chip area, we'll just grant it. And so you had that climb there up until about 2014, 15. It's kind of leveled off. And Canadians are, in terms of publication, have a competitive advantage worldwide. I mean, if you go to OFC in California, as some did a few months ago, the Canadians are there, and they're recognized for the excellence in photonics. We're going to lose that competitive advantage, I think, maybe, because there's some pretty big initiatives going on around the world now. But we're on solid ground when it comes to photonics, and some really cool stuff going on. And this is new this year. We're working with AMF, which is a facility in Singapore. And we've been manufacturing stuff with them now for a couple of years, and they were called IME previously. And we've done some commercial stuff with them as well. So we made chips at AMF for commercial purposes, like not for research in the university, but for commercial purposes. We have collaborated with them on enhancing the process design kit, the PDK, so that you can get better simulation results and better layout results. And we're partnering with Lucida and Mentor around the design automation for that. This package here is an interesting one for photonics, and we've got a really strong group at CMC, about five individuals. We've got 2 here in Ottawa, Jessica and Bob, and then in Kingston we have Herman and Nung and Dan, and I think I may be forgetting one, and Susan, who are experts in photonics. So if you're interested in photonics chip, we can help with that. And when you've made the chip, you need to package it. So we have a variety of packaging solutions, and we're exploring options around interposer technology. So interposer technology for the purposes of research, for building prototypes, for getting a form factor down of multiple chips to something. If you're building a prosthetic controller, you don't want to have a big backpack, or you don't want to be tethered to something on wheels. You want, the module to be inside your prosthetic device. And so you need that form factor would be really important. Interposer technology using, for example, silicon wafer as the interconnect. And so there's all kinds of challenges around putting in some layers of interconnect and some landing sites, and then flip chipping some chips on top of that, maybe doing the same thing on the other side, and then maybe putting a ball grid array balls on that and making it into a module. So that's not new. We've been doing it worldwide for a number of decades now. But doing it in a way that's affordable for prototyping purposes, unlike, say, Samsung that does an 8-stack memory chip that you would have in a USB key, for example, we're trying to figure out how to do it for research purposes, prototyping purposes, and then for startup purposes. So we're looking for partners around that, and that's some of the thinking on this slide. Okay, so very quickly on the last part of what we offer is around the development systems and test equipment. The Department of National Defense has this research arm called DRDC, and they have this program called IDEAS, and if you haven't heard about it and you're looking for funding, they've got $1 billion that they're investing in research in Canada, $1 billion over 20-some years, multiple mandates of government, so we'll see how that survives. But we applied for a grant, we were successful, so they gave us a contract, and we developed a platform technology that we're making available to the entire Canadian community. You guys can download it, and to the DRDC or DND for the purposes that they need. And it's a platform around AI, it's object recognition, acceleration. So our expertise in the GPU plus CPU plus FPGA, we've been able to accelerate that, and the learning, the deep learning and so on, and make it into an experimenter's platform. And so this is a visual of that, and our engineer who is prime on that, Yassine, is telling me he's getting about 10x improvement in runtime on a learning process. And so what we've done is we've purchased a cluster, and I think I've got one more slide here, and you can see some of the FPGA boards, or FPGAs that are in here, and the NVIDIA GPUs. And we've got this cluster installed at University of Waterloo as part of our program. We are nationwide, we are everywhere. So this is installed at University of Waterloo, and it's accessible over the cloud. So if you're interested in accessing a reasonably high-end cluster of 8 FPGA boards for doing a interesting experiment around accelerating an AI application or anything you want to accelerate, then pick up my business card. The secret sauce in all of this is, I mean, we can buy the boards and the CPUs and GPUs and so on, but how do you get this stack working? This is a software stack that programming environment is non-trivial. OpenCL, Python, TensorFlow, Caffe, so on and so forth. Getting all of that working, we're working with a firmware that comes with those boards and so on, has been quite a challenge, and that is what is now working for this. All right. So that's a little bit about CMC, a little bit of lines of business that we have. If anybody happened to come with a checkbook and they want to write 100K check, we've recently launched a few months ago what we call the sponsored chip opportunity, and this is where we're inviting industry to sponsor a chip fabrication run. So imagine if you are CTO for company X here in Ottawa, and you're thinking, you know, I'd like to stimulate the activity going on here in Canada. I'd like to stimulate the development of highly qualified personnel here in Ottawa. I'd like to maybe do that in the area of analog mixed signal chips in 65 nanometer CMOS, and I'd like to sponsor a fabrication run in 65 nanometer CMOS, $80,000 US there, and see some of the research going on, maybe even specify prior to the call, hey, we're interested in PLL, VCOs, I don't know, some kind of circuit. Find out who's hot in that area, Canada-wide, what faculty. Get some insight on some exceptional graduate students, super bright graduate students that I might want to hire, and stimulate activity and give back. So we have a company we're talking to right now who's in the midst of working on their agreement with legal around this, and we're anxious to announce that. But we do want to, I do want to bring it to your attention. If somebody in the room here has perhaps an interest in this, then please give us a shout. All right, so this is you're almost up, Leo. Before we do that, though, fame and glory of others. I just wanted to touch on 5 success stories. We publish a lot of success stories, and sometimes the story is the best way to describe who we are and what we do. So I'm just going to step through these quickly. So Fred Napke, second gentleman from the right in this picture, co-founded Spark Microsystems in Montreal, and they've won a number of awards. I was at ETS a few months ago, and they were recognizing him and his work. And he's working on something. I don't know that much about Internet of Things, but interesting. How did he call it? The last. This room probably full of IoT experts, but the last mile or the last 100 meters or whatever. I think he's proposing like a 700 megahertz solution because it would be way too expensive to do it with 4G, 5G, you know, et cetera, and so on and so forth. So he's proposing a chipset for that last, you know, if there was don't write this down, this is probably wrong, but if there was a 5G node in this room, you wouldn't want to have a 5G chip necessarily in this Tim Hortons cup. You might want to have a chip in here which is a much lower cost, you know, last 10 meters link, and I think that's kind of where he's at. So what did we do? Well, see under the picture here, CMC Value Adds. We provided design tools to him and his students before the startup and fabrication services, tried out some concepts, demonstrated proof of concept to investors with working parts, secured funding, and now we have Spark Microsystems started in 2016. Another example, this one's a little bit closer to home, it's at Queen's University. We have Spectra Plasmonics is the name of the startup company. We provided micro-nanofabrication lab equipment and access and engineering expertise for this one to work on a biosensor. This is Leo Belostotski, I should say, University of Calgary. So he's working on the square kilometer array. So this is like multiple football fields of antennas that are going to listen to space radio, I guess, application, radio telescope. And this guy's like an expert in low noise, analog, et cetera. And in the midst of the work that he's doing on the square kilometer array, he came up with interesting test and measurement techniques and instruments. And so he's got a startup called Noise Tech Microwaves that is connected directly to our support, and we provided him CAT tools and fabrication services to prototype his devices. So that's what Leo's done. Another one here, Colin Dalton. The name of the company is Neurora, and this is around I believe this is around managing epilepsy, so in-brain sensors. I think this is the business of flooding the brain with signals if you anticipate epileptic seizure, something around that. Don't write that down, but it's something around that. And he is super excited. He was at our annual symposium last fall and super excited what's going on. So he's looking at electrical signals, he's trying to predict a seizure, and then he's trying to prevent that. Pretty cool stuff. So we provided design tools to let him begin on that. This might be the last one. Karim has a startup, KA Imaging, 15 people there now, X-ray detector. So he's reduced the amount of radiation necessary to do some kind of diagnosis, and we provided design tools, fabrication, and engineering expertise to help him. So a little bit of a view from a startup perspective. Many of those individuals, if not all of them, were associated with a university, but of course now they're running companies. Oh, one more. Yes, this is the last one. Paul and AJ and John here in the picture. So this is a company called YetiWare, and this is not hardware, this is all software, but it's related to that AI acceleration stuff. So the gentleman in the middle here, AJ, is an expert in coding for multiple CPUs and GPUs and so on with the OpenCL language and deficiencies in that software stack. And so we provide a capability to enable them to develop that platform. So that's a downloadable. Okay, so we're getting near to the end here. How am I doing for time? We're doing well, I think. So I wrote here a couple of topics I know little about, and I'm being honest. I mean, when you're in the kind of organization that we're in, you see research going on year after year, 1,000 faculty, you see really cool stuff, and you can tell just by those startup stories. And so what I did is I kind of did a snapshot of a couple of cool things I've seen recently. And these are not endorsed by the company. They're not even really endorsed by me. They're just, they're just cool things. And I just want to share those with you. So the first is, I'm tipped off by one of the faculty members around this. So this is really interesting. If you're at all interested in computer architecture, if you've got a history in computer architecture, you probably recognize the names. John Hennessy and David Patterson are pioneers in computer architecture. There's a classic textbook by these gentlemen, Computer Architecture, a Quantitative Approach, I think, is the name of the textbook. Anyway, so they won some awards, and they had the ACM Turing Award lecture at a international symposium on computer architectures. And it's obviously on YouTube, and there's a variety of versions of that. But if you're at all interested in computer architectures, I recommend you go look at this. I know a professor who's keen about what they're thinking, and I'm going to try and describe it to you in the following. So we all know a little bit about Moore's law, running out of steam, Amdahl's law, and Dennard scaling, and so on. Look at this graph. So the light blue in the middle is clock speed, right? Leveled off, right? You don't get Intel processors that are faster than 2 or 3 gig now. They're not going to 4, 5, 6, 7, 10 gig. The gray line is, what is the gray line? The gray line is a thermal design power, right? So at the rate we're going, the thing would just melt, the chip would just melt, right? And the little inset box is also very troubling, right? Transistors bought per dollar. So you get more and more transistors per dollar, and then boom, it leveled off and it's actually dipped. So these guys are saying we're in trouble, and you've probably heard this Moore's law is an issue. A bit of a busy slide here, but I try to summarize it. So Dennard scaling is slowing, as is Moore's law. Today's processor performance has fallen 10 times behind the theoretical trajectory of Moore's law, right? So Moore's law went boom, but the actual processor performance is now 10x, behind that. In the last few years, third bullet, in the last few years, processor performance only increased 3% per year, unlike the annual increase of 50% that we saw in the earlier stages. I'm just repeating what these guys say. Amdahl's law is reared its head, and we're multiple cores. With some wins there, but naive exploitation by software writers. Software writers, oh, I better be careful what I say, right? I'm just joking. So software writers have been able to write code to make it longer and bigger, and then gigabytes of code and so on and so forth, because Moore's law is just giving them billions of transistors and tons of processing power. But if the processor performance isn't scaling anymore, then the code is going to get more and more slow and buggy, or not buggy, sorry, more and more sluggish, right? And so that's an issue. And at the same time, we're shifting from architecture of computers that are traditional desktop PCs and mobile devices, that's old, to IoT devices and cloud. So it's a different regime. And the IoT devices is crazy, right? I mean, if you want to put a chip in here, I doubt it'll ever happen, actually. I mean, we can't even agree if we want to use cardboard or plastic, let alone silicon or whatever might be in here, right, in terms of the environmental impact. So, but still, if you want to put a chip, let's put a chip in here. If you want to put a chip in a set of glasses, the power budget has to be tiny, right? Because you don't have a big volume for a battery and so on. I mean, IoT is going to really, really make it difficult to have things that can be powered. They may have to harvest power from their environment. So we got some issues going on. And Hennessy and Pedersen suggest that, bottom line, computer hardware design is back. It's hot again. And these guys talk in terms of decades, right? It's not like this year, last year, whatever. We're entering into a multiple decade era of maybe computer design and hardware architecture as a super hot topic. Maybe it's back. And they're proposing what they call domain-specific architectures. So an architecture for a class of problems. So an ASIC solves a particular issue. A general purpose processor, such as an Intel 8086, x86 derivative, is general purpose and power hungry and all that kind of stuff. But maybe we're entering into an era where we're going to have domain-specific architectures and their associated languages. And then AI is a great application for that, because you want to accelerate certain classes of problems. And they're saying, watch the lecture, and they're saying it's affordable. And when I hear that, I think, well, geez, that's what CMC does for a living in Canada. So they built their Raven chip as an example. You got a citation for a paper here. They built their Raven chips, 2.37 squared, millimeter squared, and ST 28 nanometer CMOS. It boots Linux, operates up to 961 megahertz at a 1 volt supply. This is like Berkeley student stuff. And the CMC academic price to make that chip's around $10,000 Canadian. So maybe, and it's doable with the tools we provide, the chip manufacturing services we provide, and so on. So if you add that all up, Canada has a huge AI advantage at the moment, as you know, right? Worldwide, we're recognized for that. There are some benefits to hardware innovation, because you can lock up IP, you can scale up to profit through manufacturing, and hardware lets you sort of enter into a niche and be protected by some high barriers to entry, because hardware is hard. AI has to work at the edge, right? As we put more and more intelligence into that security camera that doesn't have to send video back, it just sends information back. Like Mary has walked into the room instead of like oodles of video being watched by a security guard, right? So, but how do you get that intelligence in the end node? That's going to be a big challenge. RISC-V is an interesting technology. And it turns out Rick O'Connor, who's the executive director for RISC-V Foundation in Canada, is here in Ottawa. And RISC-V seems to be getting a fair amount of interest. And then we're around to help with prototyping and setting up collaboration. So I don't know, maybe I'm smoking stuff, but maybe there's an opportunity here for Canada. I just happen to notice, I don't know if you heard of John Cooley. He's got something called deepchip.com. So the Electronic Design Automation Conference is on right now in Vegas. It's running this week, and he wrote there this morning, he writes his guide to the conference. It's weird to see what was primarily an academic, hobbyist, fun little open CPU project has now become a serious threat to the ARM IP empire. Well, okay, maybe that's a bit of an exaggeration, but still, RISC-V has quickly morphed into something that might actually challenge ARM. ARM being the kind of world leader in processor IP and architecture and so on and so forth. Yeah, so maybe there's something around that. So that's the first thing I wanted to share with you that I really don't know that much about. And then, Leo, you're up. Okay.
You're doing a great job.
So this is the last topic. Neuromorphic chips. So these are microprocessors configured to be more like brains, human brains, than traditional chips, or brains of any biological creature. And on top of that, computing by use of light. Okay, so I don't know about you guys, but every time I see a layout of chip, I am just blown away. I mean, it literally has 1 billion transistors. Somebody literally had to design this thing. All of those transistors have to be working, or there has to be some formal method to make sure that there's a way around it if it doesn't. It's unbelievable. I mean, it's like it's like looking down in New York City or something sometimes at a chip. And now we're doing it with light. Now we're moving light around in a chip. Okay, so half the people in the room here, yeah, I've been designing photonics chips for a while, like Leo here. But there are others, like me, it just blows me away that we're actually moving light around on a chip now in order to do computing. So I'm going to try hard to show a few slides from Dr. Herman Wong at CMC and Dr. Bhavin Shastri at Queen's University on a chip that they made. And I'm going to work my way up through about 6 slides to a picture of the chip they designed. So here we go. On the left, traditional electronic chips. So this is like an SEM, and you can see wires, right? And you can see transistors, and you can see gates, and there's gate or drain and source and the channel and all that kind of stuff. And we use metal to route electrons, and we've learned over the years, decades, to make that operate up to about a gigahertz or 10 gigahertz type of frequencies. And the wavelengths are on kilometers to millimeters. And typically what we have in there are transistors, capacitors, resistors, and so on. On the right is the optical world. For those in the room who are not familiar with this, we have waveguides that move photons around. And we're figuring out ways to actually bring in active devices and actually think on the chip, as we do with a microprocessor, start to do it in the photonics realm. And so that's what I'm going to talk a little bit more about. So we can move light around in a chip through waveguides. So you look at these equations and so on and so forth. If we get the materials correct, then the light's going to go down the waveguide. So that's how we can route some stuff around. So that's useful, and you can see a picture of a waveguide in the far right there. Now, so it turns out photonics is actually quite a bit larger than microelectronics. So microelectronics, we're down to nanometers, right? So there's a 10 nanometer process that literally has features in there that are around 10 nanometers in size. There's doping, that's the addition of certain elements that you can actually count, like dozens. Like there's maybe 30 or 40 dopant atoms added to a channel, right? I mean, this in photonics, so 7 nanometer, 10 nanometers. In photonics, it's hundreds of nanometers. I think a human hair is 100 nanometers. Can't remember. Anyway, so it's a bit of a different realm. Photonics are bigger. So if you're familiar with what a filter is in electronics, like a bandpass or something, this is, Leo, I'm going to need your help here, okay? This is a filter here. So what we're doing here is we've got light moving down here. It enters into this ring resonator. If the length of that ring resonator happens to be the right length, then basically we're gonna trap that wavelength and then create a filter, right? And so you can see the diagram on the far right hand side there of some kind of band pass or I think it's a band pass filter of some kind. So through constructive interference, moving light around these ring resonators, you can create filters. You can start to modify what's going on. With lasers, you can create light sources. So this is a slide on that. I don't think I'll get into that. With active devices, you can start to modulate things. You can actually start to change the properties of that ring resonator so that you can shift its center frequency and start to filter at a different wavelength. And you do that. There's some semiconductor approaches to doing that by changing a field, et cetera. And there are some thermal methods of doing that. Yeah, there's a little, on the left-hand side bottom there, you can see heater. It's a blue structure there. It says heater there. They literally put in a resistive heater in these chips in order to change the properties of how the light is going to be filtered or manipulated or transmitted. So on the left here is a human brain, 100 billion neurons, 100 trillion synapses, an amazing interconnectivity, 1,000 input and output nodes on average for each neuron, massively parallel, so on and so forth. Reasonably slow operation, right? About 1,000 operations per second, like 8 kilohertz. Power consumption, 10 watts. 10 watts, it's like slightly warm if you touch. Like imagine a 10-watt light bulb, like a couple of Christmas lights, the old traditional Christmas lights, right? On the right-hand side here, we have some supercomputer from 2018. It's 13 megawatts on the bottom right there. And it's good at kind of a repetitive thing, right? So it would do math well. This thing on the left here would compose a symphony. It's fascinating, right? Anyway, so there's a little bit of difference there. So on the neuromorphic computing, what we're going to try and do now, we're going to try to mimic some of the functions inside the brain. So we have here a neuron on the left, and we have multiple inputs. Each of the inputs is weighted by a coefficient. We're going to sum those weighted inputs, perform some kind of nonlinear operation, and then send the output to other neurons. And so you can see the nature's way of doing it on the left, and you can see a mathematical representation on the right there. And if you build a system of these, then you can start to build a learning network, for example. And with that, you could show it cat pictures 10,000 times, and then show it a 10,001st picture and say, what is this? And it should say a cat, if you can teach this deep neural network. So how could you mimic that basic human function in photonics? And this is where Leo takes over. No. And so what we have here, photonic weighted addition. And so on the right-hand side there, you can see a series of those filters. And you can see the arrow through them. They're all tunable. And you've got a detector on the output. And so you can program this thing with coefficients, with weights, okay, to act as this thing on the left does. And then for integration nonlinearity, you can go through this semiconductor stuff on the bottom right here, which I'm not going to explain. So building on that, you can make a chip. And so here it is, finally. This is the photonic neural network chip. It's super simple, right? So for general orientation, the little purple boxes all the way around at the periphery are the electrical contacts, right? So we're going to bring some bonding wires in there and send electricity in or electrically sense what's going on. So that would be for programming it, for applying power to those heaters, for creating those fields and so on, for setting weights and so on. You need to send light into this thing, and that's what, I'll just point to it. Those are the light waveguides, so you need to couple vertically into the chip with a light. And then you can see on the upper right here a single neuron, and you can see a series of those filters with a light coming in and then some electrical stuff in order to do the weighting. So this is basically it. Now, okay, how close are we to the human brain? Well, this is just a single neuron. This is like, what, 8 neurons, right? This chip has 12 neurons. So it's not even close to a brain. But it's fascinating, right? So we're doing computation in silicon with light modeled of the human brain. Pretty cool. So this is some bleeding edge stuff. It's quite exploratory in nature. It's not going to be in something that's going to be under the Christmas tree next year in terms of a product, but it's cool stuff. And that has to be tested. So there's a little bit around that. How would you design it? So you would use device-level design tools like numerical, the Lucida Python scripting tool, the Tenor L-Edit layout tool. These are all tools we provide from CMC. You want to make sure the design is DRC correct, design rule correct. What that means is that if I send it in, will the manufacturer be able to manufacture it? So that's what the design rule checking box is, or line there, number 4. And then you want to do some checking to make sure it'll be testable. And that's non-trivial because you got a left-hand side, you got to bring in some light. In the middle, you got to drop in some electrical connectors. And then you might choose to do that with wire bonding to stimulate this thing and measure it. And this is the test bench for testing the chip. So this is kind of a diagram of what would be involved in testing this. You know, you've got a variety of instruments all the way around here to provide the stimulus and to measure. Okay, so that is my presentation. CMC helps with chip design, with chip manufacturing and chip testing. Tried to provide a little bit of background on the types of organizations, universities and colleges we help, startups we work with, a couple of cool things we've seen along the way. If you've got any questions, Leo's available.